Hello everyone, my name is Dominik Wiedenhofer. I'm a senior scientist at the Institute of Social Ecology at the University of Natural Resources and Life Sciences in Vienna, Austria. And today I'm presenting some work we have been doing together with some great colleagues from the Earth Observation Lab at the Humboldt University Berlin, Germany. And the paper I'm presenting actually just got printed in Environmental Science and Technology. So what have we been doing? We have been developing a novel approach for mapping material stocks of buildings and infrastructure from remote sensing data. And I want to show you what we have been doing here. All of this work happens within the context of an ERC Advanced Grant project, which is about understanding the role of material stock patterns for the transformation to a sustainable society, focusing on the stock flow service nexus. So what we are specifically interested in is to understand the different relations, outcomes and efficiencies of socioeconomic stocks like buildings, infrastructures, machinery, between the flows, the energy, the materials, the waste and the emissions, which are all related to building stocks, operating stocks, maintaining them, replacing them. And most crucially, we want to understand what are the services as an outcome of both stocks and flows. So obviously there will be different relations. If you have a highly efficient passive house buildings, you will have a high quality of living space and require very little flows. In other cases, it might be better to have more flows and less stocks. So there will be trade-offs and there will be different levels of service quality. And we think that the services are actually the contributions to social well-being that we are all interested in. And we would also say that a sustainability transformation require reconfiguration of the stock flow service nexuses to achieve higher well-being for all at much lower levels of resource use and emissions. So this is the context of our work. Mapping is an important aspect for us because clearly the spatial patterns of material stocks are a key factor for the material and energy flows required to preferred services. Think about dense urban settlements versus sparsely settled suburbs. There is clear differences in the spatial configuration and also in the flows and services coming out of that. And understanding spatial patterns of stocks is key for issues such as urbanization, spatial planning, secondary resource management, urban mining, and so forth. And in our field of industrial ecology, there have been a lot of efforts to map material stocks. Mapping them requires encompassing knowledge of the built environment. So one needs to see and map infrastructures, buildings, building types, building areas, building heights. So there is lots of dimensions of stocks involved which need to be understood and mapped and quantified to be able to provide these space to look into these spatial patterns. And so far in the literature there have been two major approaches. The first is highly detailed cadastral data and official 3D city models, which are clearly an ideal source if you have them. So on the right hand side you can see such a screenshot of a 3D building model. If these are available, obviously these are a great source to estimate material stocks and look at patterns, but these are often only available for a few selected cities or maybe some regions. It depends very much on the national open source policy, open science policies, if this data is actually available or if it's actually very expensive. And as I said, it's often not available for many areas of the world or for non-major cities. So also people have been using nighttime lights to map various socioeconomic issues, basically correlating them with the intensity of light. You can see here on the right hand side such a map for Europe. However, this kind of data is actually spatially quite aggregated usually. And also obviously you can quickly imagine that their nighttime intensity is correlated with some aspects of stocks quite well, but with others probably much less. So there is a lot of inaccuracies here to be had. What we thought here in our project is we want to actually go beyond that. We want to try a new approach building on the latest generation of Earth observation data available. So here you can see the workflow of our model. I will run through the details in the next slides, but just as an overview, you can see on the top that we have been using Earth observation data from the Sentinel missions of the European Space Agency. We have been using crowdsourced data from OpenStreetMaps, which we then combine to understand the built-up areas, to understand the sealed surfaces due to infrastructures, to model building heights using also additional reference height data. And from these information, we can derive the dimensions of the stocks that we need to then estimate the material contents using material intensity factors, which we developed together with a lot of national experts. So how does it work? So firstly, Earth observation data, optical Earth observation data from Sentinel-2 is the newest mission of the European Space Agency. These are high-resolution data with several spectral bands which are mapping the planet at a very high intensity and at a very high resolution. You can see here the satellite flying around the Earth and providing lots and lots of pictures. You can imagine that this is huge amounts of data. So we have been, or actually our colleagues have been using the Vienna Scientific Cluster, a supercomputer, to crunch all this data and to derive actual a map for a year, basically, because you need to correct for cloud cover, you need to correct for all kinds of issues to be able to actually have a robust data set here from all these layers of information and many flyovers of the satellites. Then we have been also been using radar data from the Sentinel-1 missions, which is not affected by cloud cover, but which has a few other limitations and attributes, which my colleagues would be able to tell you a lot about. Basically, the idea was that this is information which gives us radar backscatter and shadows from buildings, basically radar shadows, so we can estimate building heights using this additional data source. So in terms of Earth observation data, we use the Sentinel-2 missions, as I mentioned, very high spatial resolution. You can see a screenshot there. We use the Sentinel-1 about surface roughnesses and also about radar shadows. And we use the OpenStreetMap directory for line infrastructures such as roads and railways, also subways, tunnels, bridges, which are very hard to catch actually from a satellite. That's a lot of data crunching already, as you can imagine, and has taken a lot of effort to make this useful. What did we do here exactly? We have been building on some previously published or recently published work. So firstly, one needs to identify the subpixel shares of built-up areas for each single raster cell in a map. So we did this using a machine learning-based regression approach, which was trained and validated by manually labeled reference data. We used the support vector regression model to estimate building heights from the combined Earth observation data, which was trained on several highly accurate open source 3D building models available for some cities and regions in Germany. Then we did a classification of building types based on the morphological metrics from Earth observation satellite data and used a random forest classifier to derive building types also here, and training samples were also manually collected for this purpose. And then bridging the remote sensing world into the industrial ecology world, we developed 5 building types, 21 infrastructure types, 13 materials, and the material intensities together with national experts and from the literature. And now I want to show you some results. So this is the novel high-resolution map for Germany and Austria. You can see in blue there is very little or no stock, and in red there is a lot of stock. Not surprisingly, the cities really jump out of this picture. You can also see that the smaller settlements and the mediumly densely settled areas in for example, in Western Germany, the Ruhr district or Frankfurt area, and you can see very distinct patterns, and you can also watch these on the right hand side. You can see a web link. You can also look at this data actually with a web viewer. So this is the overall aggregate map that we have been producing here, looking at residential buildings, commercial buildings, and road, railway, and other infrastructures. You can also zoom in. So this is a zoom into Vienna, the city where I actually work and live. You can see here very clearly the subway lines, which are very materially intensive in the red lines, which also correspond to major highway arteries of the road network. You can also see the building structures here in red to orange, and in the blue you can see the surrounding forests and agricultural areas which surround the city. And you can see very nice patterns here, and we hope that this is really useful for further analysis. And from this kind of data we differentiations into 5 building types, 21 infrastructures, 13 materials. So here on the right hand side you can see always from the top to the bottom the same spatial location, so dense urban Berlin on the top here, and then you can see basically the single layers, so the single family houses in that region, the multifamily houses, the commercial industrial, the roads, the railways, subways, and other infrastructures like that. And similarly for other regions, you can see here, for example, this is industry commercial. This is actually the airport and parts of the oil refineries close to Vienna. The roads networks here in this area, and you can see a lot of detail that we can actually display. So what's the key novelty here for us is also that we provide a very high resolution. So on the left hand side you see what the highest resolution that we have, which is on a 10 by 10 meter scale with subpixel information, and you can very clearly see the outlines of infrastructures, of buildings, of blocks of buildings. You can see the roads in there. So that's very highly detailed information, which we think can be really useful for further applications in all kinds of questions. And just to show how this translates, we took that same screenshot or that same part of the map and aggregated it. So in the center you can see what happens if you aggregate to 100 by 100 meter resolution, and what happens if you aggregate to a 1 kilometer per 1 kilometer resolution. You can very quickly see that basically most of the patterns get lost when you aggregate the data. And most of the nighttime light data, which is widely used to map stocks, actually, it is somewhere in between the 100 and the 1 kilometer resolution. A lot of it is actually at the higher resolution even than the 1 kilometer. So you can see while it might be feasible to downscale or to map patterns here, you cannot really actually make out the real patterns of a city or of settlements and infrastructure patterns. So we think that this high resolution is really a huge step forward for mapping stocks and for making that kind of knowledge useful for all kinds of applications. So the next steps after Germany and Austria, we are currently working on the United States, the UK and Uganda to apply our methods there. Each country has specific challenges which enable us to further refine the method. So obviously the training data is really important, the underlying information, if there is 3D city models available, what kind of open source data there is, also what kind of infrastructure data is really robust, what kind of material intensities can be developed. So all of these questions always depend a little bit on each country in its own. So in that sense, we are really looking forward to seeing how far we can push the method for these next steps for these other countries. And overall, I would say that the last 3 years working with the colleagues from the Humboldt University, from the Earth Observation Lab, was a really intensive but very rewarding interdisciplinary collaboration, which was necessary to bridge remote sensing and industrial ecology. We think the novel high-resolution method yields comprehensive maps, including infos on dimension, types, items, materials, which I think is really useful for a lot of applications. We cannot really rule out overestimations. We did a lot of cross-checking, but other methods also have their limitations, so it's really hard to say what is the exact or the true result. I think that's a very big question. We think that our data is really Useful because it can be applied on very large scales, but as I said, the required underlying data is not so easy to get by, and other countries will help us